Good evening to everyone. Myself, Dr. Suresh Kannaujiya. I am faculty in Geoscience Department, IIRS ISRO, Dehradun. I am going to take a lecture on satellite navigation, and I will cover some of the very traditional method of navigation. Then I will followed by our this new satellite mission for navigation, like starting from GPS, GLONASS, Galileo, Bedu, INSS, QZSS. So these all are basically the part of global navigation satellite system. So first we have to understand what is satellite navigation. Means what is navigation? Why we require this in our life? Why the user need this? So you know that for example, for instance, when this fisherman is going into the ocean, so they need to navigate themselves so that they cannot cross the border, international border. They cannot go such a distance so that they will not track back to their original location. So earlier, before this era, instrumental era, people used to use this traditional method to navigate themselves. So and so that they can follow the path, and so that they should keep some reference, like your stone, some trees, like that. So that means I'm talking about on land. So that they can remember those reference this item, so that they can trace back, and they can relocate themselves and comes to the original location. So nowadays, and then this nowadays this navigations has been emerged not only in the regular life, like in means vehicle, aircraft, defense, and some this research, like your atmospheric research, upper atmosphere, lower atmosphere, then cloud study, then radio occultation, then tectonics, then geodesy. So it has immense applications these days, and it has completely revolutionized in the navigation field. What our this legacies given by the Babylon and other this civilization. So first I will try to show you some history behind the mapping and surveying. So you can see this. The first map were mental maps used for navigation. So the this some civilization has used the mental maps to navigate this, to get the some map prepared, so that they can get the this location, some area, some road, some etc. can be navigated with the help of all these things. Then this Indus civilization has proved that it has a underground drainage system. Then about 5,000 years ago, Babylonians produced property descriptions and simple property maps on stone tablets. So this shows that this is not us that we bring in navigation. It is our ancestors and others these civilizations which already developed all this technique long back, and now we are living in the instrumental navigation system. So this you can see first known surveying by ancient Egyptian used to re-establish property corner destroyed by flooding of river Nile. Then about 2000 to 2500 years ago, Greek and Romans surveyed and mapped their new settlements with a great degree of precision, using methods that change very little up to this century. Then the various instruments which used for these navigations and other mapping and surveying are chain, tape, cross staff, optical square, theodolite, tachometer, compass, levels, EDM, electronic distance meter measuring, total station, global positioning system, our global navigation satellite system. So these are the total instruments which are currently utilized for mapping, surveying, and navigation. So the classical method, this triangulation and trilaterations. So earlier, before the instrumental era, there was a triangulation method, which was angle-based location measurement, and not only the measurement, but for surveying and mapping as well. So apart from providing the location of any point, this triangulation method were used by the theodolite and all to do the mapping and surveying. And it is, you can visit Survey of India, and you can get the example of triangulation method. So it is our legacy actually. And the trilateration is new, and our instrumental era means GPS and GNSS is mainly working based on trilateration. So trilateration means distance measurement. So distance is getting measured between satellite and your ground antenna. And after that, once we have three distance, so with the help of that we can get the three unknown x, y, z. And if we have a four distance, then we can get one more unknown solved, that is your time, accurate time. So in nanosecond, which can be in nanosecond accuracy. So then the first this satellite launch on Earth, it is by Russia, and means Sputnik 1, and in 1957, then October, and then followed by Sputnik 2, and then 1958 Explorer 1 come into the picture. And then after that, with the help of this mission, and we came to know about the Earth flattening. Earth flattening is basically defined by the your equatorial radius minus polar radius upon equatorial radius. So it is basically define the shape of the Earth, our shape, same plane, so that we can use it and we can correlate with other data set as well, because all this data set you have to bring on a common plane. So these are the earlier data, and this is with respect to your, I think this is one of the datum, this geoid 1993, like WGS, World Geodetic System 1984 datum is there. And there is different series is there, like ITRF series is there, ITRF 2000, 2005, 2008, 2014. So 2014, ITRF 2014 is the latest and very precise datum. And how this ITRF and new WGS 84 is getting means more reliable and more precision because of the gray satellites. So this all comes in the part of geodesy actually. These are the part of geodesy. So like that gray satellite mission, like GOES, GRACE, then your CHAMP, all these are the your this geodesy mission to get the accurate gravitational potential around the Earth, so that we can estimate the accurate geoid. And what is geoid? Geoid is the equipotential surface all around the Earth, and then we derive the ellipsoid with the help of geoid, which is the mathematical surface. So then in 1993, this lambda least square ambiguity decorrelation as adjustment come into the picture to resolve the ambiguity, which is very very critical in the navigational data, so that we can resolve this ML and this Menbol, this other this from the raw navigation data. Then other this landmark is there, landmark based navigation is there. So it is stones, trees, monument. So researcher and users use this technique to locate themselves and to get the precise location. Then celestial navigations come into the picture, but it is good for latitude determination, but poor for longitude determination. And longitude basically varies in east-west direction, and latitude varies in north-south direction. So then, how we can accurate get the accurate idea about the longitude? So then, clock come into the picture, and it is accurate clock come that was quartz clock followed by atomic clock, that is cesium and rubidium, and it is very much operational right now in the satellites, various satellite mission. And this first accurate clock invented in 7060. Then there were a revolution in this. You can see the 13th century magnetic compass come, which give the magnetic north, not the true north. It were giving the magnetic north, but this 1907 gyro compass come into the picture, and it started giving the true north, geographical north of the earth. So this was the difference between magnetic compass north and your gyroscope compass. Then 1912 your radio direction finding come, and then and these all were very much utilizing by these ships, because in earlier days transportations were mainly dependent by the ships, and these days also. So these cargo ships are there, which are carrying so many. They are means giving so much contributions in the economics for their countries and all. So like that, this 1940, 1950, this Lauren AB, Lauren C, all this low frequency radio based mission came into the picture to for this ranging and navigational this determination. Then 1960 this Omega mission come, and it was also. So these are the various evolution which were taking place over the time. And then the first development of GPS took place in 1980. Means people were this researchers started talking about that we should have this GPS now. So then 1993 the first GPS launched on 8th December, and then 1993 followed by this GLONASS mission come into the picture. Then 1994 this international GPS service, means IGS, began. Now it is GNSS. So this 2000 in 2006 this GNSS conceptualization took place. Means various navigational this constellation which are operating together in all around the earth, they were contributing together to give the very precise location, and they are, because of their more coverage, less DOP. So I will talk about what is DOP and PDOP, TDOP, VOP. I will talk about all this thing so that you can get an idea, because this is the fundamental lecture, and I will have this more detailed lecture, and followed by advanced processing of GNSS data in the subsequent these days of this particular module. Then 2010 this GLONASS again resume, and then QZSS also started constellating these satellites into the space to provide the regional navigational services in their Japan and nearby territory. Then your 2013 IRSs they have come into the picture, and this total mission duration, this 2013 to your right just now this your launch has been completed, and it is completely IRSs is completely operational now. And IRSs is known by another name also, it is called NAVIC, and it is given by our PM, Honorable PM, and it is called Navigation with Indian Constellation. And IRSS full form is Indian Regional Navigation Satellite System. Then in 2020 Bedu constellation started, and Bedu is also operational. So right now, apart from this IRSS and this QZSS, these two are regional navigation satellite system. But the other constellations like Bedu, Galileo, GLONASS, GPS, these are global navigation satellite system, and they are providing regional navigational services. So here you can see the different accuracies providing by different mission. So this GPS is providing 15 meter, and this is earlier. Right now these days you can get better than that because augmented GPS is there, so it is giving better this accuracy and precision than Lorenzi, then this transit, then Taken, then in this inertial, then Omega. So these all missions means evolve over the time, and now GPS is most accurate mission, and very soon IRNSS will be available in all the users mobile and all. And right now it is coming with Redmi, and I will show you some of the information. So this is E-LORAN system concept. So this is very unique, and this is not a satellite mission. This is you see, these are the transmitting station. So there are some transmitting stations, and there is a control center. Then there is a monitoring sites, and where these data are getting monitored, so that this if there is some more ambiguity and more error, so that it can resolved at the monitoring side with the help of control center, and it can retransmit to the station, so that these users can use the accurate data to locate and to navigate themselves. And it was providing by your telephone, car, your ships, and your aircraft. Then these are the global LORAN coverages. You can see how these coverages are there. So it is available in pockets. You can see. So these are the thing. So very few available over the Indian region. And this is the US LORAN system. So very systematically this monitoring and setup all over this US. Then these are the timing and frequency overview. Then this is the European GNSS Service Center, and this is about NAVIC. So as I told you, NAVIC initially came, it was a joint venture between ISRO and this Redmi, and this chip was developed and it was embedded now with the Redmi phone, some of the Redmi phone. So chip is like this, and there was a project called Dhruva, and it was funded by the Ministry of Electronics and Information Technology, and with Samir, Society for Applied Microwave Electronics Engineering and Research, as the nodal agency. The research also interfaced with the Space Application Center of the Indian Space Research Organization. So these all about your Dhruva, the development and all. These are the team who developed who has contributed in the development of the Dhruva. And with the help of this map My India NAVIC, you can use this NAVIC signal, and this is mainly for this fisheries actually. So this is developed for this to enhance the this navigational this system in fisheries. And these are the geodetic toolbox. You know, this GPS is the one of the geodetic toolbox. So there are some other toolbox as well, like INSAR, so microwave mission. Then photogrammetry is one of the geodetic toolbox. Then borehole strain meters is one of the toolbox. LIDAR is laser interferometry. Then this GPS, then Grace mission. So these all contribute together to provide the very good geodetic information all around the earth. And this is the one setup campaign setup of this GPS campaign. So you can see this satellite sends a signal that can be used for positioning. So these are the satellites, you can see that here. This is antenna choke ring antenna, and the signals are received by this GPS antenna, and then this is your housing where your then solar panel is there, then some this transmitting antenna is there, then your receiver is inbuilt inside the housing. So this wireless communication sends the data to the data center. So this is the complete setup to get this GPS data to the data center from this location. So like that, and this is not very robust setup. So there is a robust setup, like there is a complete monument where the antenna has been set up, and continuous this data transmission is taking place with the help of these wireless communications, like your some VSAT is there. So VSAT is basically data transmission is taking place through satellite. So this is one of the example, this tectonic geodesy, so which determines the position of tectonic geodetic monuments and monitor how position change over the time. So when this instrumental era came into the picture, so this tectonic geodesy needs millimeter accuracy, and it should be fixed, it should not be dynamic. So this this r square should be very close to 1 when you are getting the standard deviation. So it should be close to r square should be 1, close to 1, so that you can get very accurate information about the tectonism which is taking place between two plates. So it gives a very good idea about the intraplate deformation, interplate deformation. It gives a very good idea about the subsidence, active fault information, whether the fault is active or not, and some and these days and this managements are using this technique, and they are setting up on the buildings and on some very good heritage buildings, so that they can track this deformation, vertical deformation and horizontal displacement. All these are getting very conspiciously monitoring by with the help of this instrument GNSS data. So earlier people were dependent on this tectonic geodesy with the help of VLBI, very long baseline interferometry, uses the difference in the time when the radio signals from distant quasars, means celestial object, arrives at different points on the earth. Then this satellite laser ranging SLR came into the picture and uses time required by the light from the ground based laser to bounce off satellites. So it is also operational these days also. It is not that it is top. This VLBI and SLR both are operational, but it is mainly for the corrections of the GPS or GNSS data. So because these are very costly affair, so that's why it is not possible for the common users, but it is mainly utilized by these research agencies to get this orbit data corrected, your ephemeris corrected, and your mathematical path of your satellites can be precise with the help of all this information. And this basically using the two-way travel time measurement SLR, so that they can give the precise location of the earth or some point on the ground. So this is global positioning systems. This is the new and latest, and relies on the travel time of radio signals between satellites and ground stations. So GPS basically, this is one way system. So this is only transmitting, and radio signals are in different frequencies, L1, L2 and L5. So for instance, so there are some other this GLONASS is using some different means they are using L1, L2, L5, but of some different numerical value. So like here GPS is using 1575 L1, L2 is 1227 megahertz, and L5 is 1176 megahertz. So these all are falling in L band of microwave range spectrum. So this is how GPS is working. So they are transmitting code wave, carrier wave. So code wave is nothing but it's a square wave. So it is very good to get the instantaneous position, pseudo range. but carrier waves is very good for those who is looking centimeter or millimeter accuracy. So for those, carrier waves is very good because it carries a phase informations. So this amplitude and this all these are changing with respect to time, but in case of square wave, it is only changing in 0 and 1 with respect to time. So that's why it is very difficult to get an idea that if something is going to happen when they are traveling from the satellite, which is placed at 20,200 kilometer, for instance GPS, and for your IRSs it is placed at 36,000 kilometer because it is GSO and your geostationary orbit and your this geosynchronous orbit. So these are the orbit where the IRS satellite has been placed, but GPS they are placed in MEO, medium Earth orbit, and it is around 20,200, and they have 6 orbital plane. But here this and other constellations, they have different orbital plane, and where they have kept different number of navigation satellite. So this then what is happening, this GPS is continuously sending this L1, L2 and 5, and this ground antenna is there, or your mobile is there, and it is receiving these signals. And what is happening on the same time, your mobile or your this thing antenna means receiver producing a replica signal of at same time. So at and this signal is these are radio signals, and they are propagate traveling with the velocity of light. So but you see when they are coming from satellite to the earth means ground, so there are so many layer, like ionosphere layer is there, troposphere is there, then some more corrections are there, like your clock error is there, orbit error is there, then multipath error is there. So so many ambiguities are there present. So that's why we receive when this signal interact with your this receiver, so which is producing a replica signal, so it should get match. So if it is getting 100% match, means if there is no error, so it means it is estimating the true range, but it is not happening actually. So because of this all these ambiguities, so which is present between satellite and your ground antenna or ground receiver, so that's why your this you are getting a pseudo range, and it is not the true range. So then once you apply all this error budget on your data, so you get the accurate information about the your this L1, L2 and L5, and subsequently it is very accurately estimating the your distance between the antenna, ground antenna and satellite, then followed by you are using the trilateration method to estimate the latitude, longitude and ellipsoidal height. So this is also called Cartesian coordinate, geocentric coordinate, geodetic coordinate, or this polar coordinate. So various transformation system are there, so in which you want to estimate the coordinate, you can do that. So most accurate is geocentric coordinate, where you are using the center of the earth, and then you are getting the latitude, longitude and height. Then this geodesy for tectonics and earthquake studies. So you can see geodesy is the science of the earth's shape, and find precise positions, monitor changes due to tectonic process. So various tectonic processes are plate motions, boundary deformation, interplate deformation, earthquake cycle, volcanic processes, land subsidence, etc. So this is one example of this current era, how this satellite navigation is being utilized immensely in this application. So these are the satellite constellation, like Galileo, this Japan QZSS, then GPS, then GLONASS, Russia, then IRSS, then China Vedu, and this is the specifications of the various constellations. So you can see these are the constellations. So China are using two orbit, geostationary orbit, then IGSO, inclined geosynchronous orbit they are using, and they have placed their satellite at this altitude, and they are also using like GPS, this MEO, and they have placed a little bit higher altitude, 21,000, and then Galileo is using a little bit again higher, 23,000 and 22 to 222 kilometer, and India is using 36,000, and then Japan is also using a little bit lower this thing, 32,000 kilometer. This is also GEO only. Then period is here, means complete one period is complete one orbit is taking place around 12 hours, here 11 hours, here 12 hours 38 minutes, and then in European this 14 hours. Then India is working on sidereal day, because this is in GEO and IGSO, so that's why it is working on sidereal day, 23 hours 56 minutes and 4 seconds, and this is also 23 hour and 56 minutes and 4 seconds sidereal day. Then the satellites 32 operational, here GPS. So not all are this thing, some of them are in spare, and some are in, because there are 6 orbital plane, so that's why some satellites has been placed so that they can get this tracked at least 4 satellite in the antenna and receiver. And in Russia 24 is operational, 2 in testing and 2 in maintenance. So you see China is having the maximum operational, 45 plus 5, and Galileo is having 24. India is having 7 operational, because this is regional, so that's why it is having less number of satellite. And then QZSS is having 4 operational. So these are the orbits. Then these are the frequencies, as I told you, L1, L2 and L5. So for GLONASS it is called G1, G2, G3, and for Beidou it is called B1, B2, B3, B2 and B3. So you can see they are representing in gigahertz. Here they are also representing in gigahertz, and then European is also representing in E1, E5 and E6. So these are the frequency, and here the this difference is between Navic and other constellations. So Navic is also using L band, but here it is using other frequency it using is S band. So it is 2492 megahertz, so very high frequency in microwave range. So this is very unique, and so to improve this travel or this propagation when it is traveling through the ionosphere layer and some other your mission purpose and objectives. Then Japan is also transmitting in L band only, 1176, 1277 and 1575 megahertz. These are the frequencies, and one more new frequency has come into the picture, 1278, that is called L6. So this is but they all are transmitting in L band only, apart from this S band which is in Navic. Then these augmentation systems are also there to provide very good signal to this aircraft and defense services. So VAS is there, then SDCM is there for case Russia, then BDS BAS is there for China, IGNOS is there for Europe, Gagan is there for this India. So this was launched a long back. So it is also called GPS added geo augmented navigation. Then SMS is there for Japan. So basically like Gagan is using the GPS signal, and they have set up the ground antennas, and the ground stations are there, and they are acquiring the data, and they are means improving all this error, and they are sending back these corrections files to the these satellites launched for this to receive the error and to send the this defense purpose and to the aircraft. So that is called, that is your GSAT 8, 10 and 15 GSAT. They are these are the satellites where they are sending receiving this corrected signal, and they are sending back to the defense and the aircraft. So then this vertical accuracy and this horizontal accuracy is getting enhanced because you this and this was the joint project. Gagan was the joint project between AAI and ISRO. So after that, this it is very much operational in AAI, and they are using this signal in their aircraft. Then early space this based radio navigation systems. So this launch of Sputnik was there. Then it and this people researcher were using Doppler shift to measure the this distance and this navigation purpose. So Doppler shift was there, but it was a little bit complicated, and because and also the altitude was 985 kilometer, revolution period was 98 minutes. Then suggested to invert this problem, and this so that this that's why this transit come into the picture. And then and it was helping in cyclone and other applications. Then this navy navigational systems our transit used observed measurement in Doppler shift to calculate the distance and position to the satellites. And FX requires 40 minutes for a static user 2D, so it was taking long time to fix the 2D and this is latitude and longitude. So that's why this various development came into the picture. And this ultimately this radio navigation systems assisted in crustal deformation also, as I told you, and determination of connection between the most important geodetic datums to plus minus 50 meters by 1970. Then so this was there. Then satellite navigation. So as I already explained you about the global satellite constellations and regional satellite constellation. So these are the various evolution of the satellite in GPS carrier, and this is the orbit. So you can see this orbit will look like this from this latitude 35 degree, and if you are looking from this pole, I think, then it will look like this. Then in 1973 this Navistar means navigation and satellite timing and ranging global positioning systems developed, and then resulting this Navistar GPS, and in 1985 defined. It is an all-weather space weather based navigation systems development by the US DOD to satisfy the requirement for the military forces to accurately determine their position, velocity, and time in a common reference system. So as I told you, this is this can work in any weather conditions, because this is using the radio wave. So radio wave falls if you see the electromagnetic spectrum, it is on the right side of the this. If you are seeing the low frequency, so it will, if it low frequency is going into the right side, so it is on the right side radio frequencies. So it falls on the this low frequency electromagnetic spectrum. So it is very good, and it get very less attenuation, it get very less this scattering also when it travels through your precipitation, through cloud, or through this other hindrance, and it very smoothly enter into the this all this medium, and it reach to the ground. So that's why this particular electromagnetic spectrum is very much beneficial for this such application and technology. So this space versus ground based navigation systems. So this is all always a debate. Debate is there. So high frequency short wavelength radio signals is there, necessary for optimal atmospheric penetration and requires line of sight transmission path, and ground based systems are limited to object above ground. So like there are so many ground based systems are there, so where they need a line of sight to get this signal traced from one object to another object. But for case this global positioning system, so you don't require any line of sight. So if you are standing somewhere on the ground, and if you have opened your mobile, our your this campaign antenna, our receiver, and you can get this say this signal from this different satellites. And the condition is what this azimuth angle and elevation angle you have kept to means lock your this satellites. Because if you have kept this suppose you have kept 30-degree elevation angle, and azimuth is also like that. So if satellites are available on less than 30-degree elevation angle, so it will not be captured by the your mobile or your antenna. So it will be very very difficult so to get the means good number of this data, so that you can reduce the ambiguities from the raw data, so that you can get the latitude, longitude and height. So it is always necessary to what elevation angle and azimuth angle is you are going to keep, because these are the two parameters with the help of you define the position of the satellite in space: elevation angle and your azimuth angle. So elevation angle basically you means define references from the datum or a horizon. So horizon from the antenna, suppose this is the antenna, so from the horizon you are this is 0-degree elevation angle, and it is increasing toward the upside, and here it is 90-degree. But in case of azimuth angle, this is it is always start from north, and this is 0-degree, then this is your 90-degree, then 180-degree, 270-degree, 360-degree, so like that. So your azimuth angle goes like this, and your elevation angle, it only varies between 0 to 90-degree. So from all directions, from here 0 to 90, from here 0 to 90, and from down also 0 to 90, and here from 0 to 90. So like that your elevation angle varies. So wherever your satellites is present, so it means your this coordinate system, and you have to define the very optimum value, so that you can track and you can get maximum satellite data in your antenna. So this is the 24 hours 15-degree mask. As I told you, 15-degree elevation mask is there, visibility is there. So these days you can see minimum 25 satellites are present in this image, and maximum it is 50. So you can see this dark here, 50 is some of the locations, it is tracking 50 satellite, and here it is tracking 25 minimum satellites. So you know these days Betu is operational, so here, and it is mostly available over this territory, so that's why this maximum satellite is reflecting and visible is in this region than in this region. So what is GNSS? GNSS is basically the worldwide position and time determination system that includes one or more satellite constellation, aircraft, receiver and system integrity monitoring, augmented as necessary to support the required navigation performance for the intended operation. So GNSS is the result of a recognition by the civilian community of the benefits that can be derived from the development of a true civilian global positioning system. So these all are there. So, and these are the different your augmentation system you can see. different constellation, different augmentation system are there. So then advantage of GNSS, it increases the availability of the satellites and signal, markedly increase the spatial distribution of visible satellite, then reduce the SDOP, horizontal dilution of precision, and vertical dilution of precision factors, better atmospheric corrections, decreased occupation times, means faster RTK results. A larger satellite constellation also improve the real-time carrier phase differential positioning performance, than accurate, robust, and reliable services even in bad condition. Less expensive, high-end services. So these are the few of the advantage of GNSS. Then GPS, GLONASS, Galileo, Beidou, the general characteristics are. So you see this. These are the real time this user information, how much satellite it is tracking. So you see this is it is not same everywhere on the earth. So as these satellites are coming and going in each orbit, you see. So these are the 6 orbital plane, for instance GPS, and this is one way travel, as I told you, and here it is replica signal is producing here, and it should get matched, but there is a time delay due to this ambiguity. So you have to reduce the time delay. So once you reduce the time delay, you will get an idea that what is the distance, accurate distance between the your satellite and antenna. So this is the principle of GNSS. And then this navigation is basically 10 to 20 meter accuracy, means your radius will be, you will be in 10 to 20 meter radius your position. So and this was coming with the course versus acquisition this data, but now civilian code is available, and this civilian code is more accurate, and it is giving more this accurate this latitude longitude, means less than 10 meter also it is possible these days with the help of this in mobile itself you can get because of these GNSS. And velocity is better than this 10 centimeter per second. Then time is you see 15 nanosecond currently, so it is very accurate time we are able to get with the because of GNSS. Then this 6 to 3 orbits are there, worldwide coverage are there, then 24 hours access are there, common coordinate systems. Then WGS 84 it came into the picture, because when you are going to get your this latitude, longitude, and height, so it is with respect to some plane. So the plane for your latitude is your equator, precise information about the equatorial plane, and how we are getting it because of GRACE data. We are able to get the very accurate information about the equatorial plane than the your prime meridian. Then prime meridian also we are able to get very accurately, and it is basically utilized, this prime meridian plane, it is utilized to get the precise information of longitude. So we are getting our longitude with respect to this prime meridian. And then what about vertical this height? So we have the ellipsoid. Ellipsoid is mainly derived from the geoid. So this ellipsoid it is using to get the precise information about the vertical height, that how the vertical height is fluctuating over the time. So all this can be monitored very accurately and very precisely, and with fixed solutions, means 95 confidence level. And I will cover this lecture in subsequent this over the time. I think on 29th this month I will take a lecture, so I will explain you. So this you can do very nicely. So you can see here the various these constellations and their positional accuracies, velocity accuracy, time accuracy, the this PRN. What is PRN? PRN basically the designated your pseudo range number. So all satellites has been given a name. So this, and we call by their name only. So that, for instance, this pseudo range number 4 means this is for satellite 4, like this Cosmos, Zio, Vedu 1A, like that it is there. Then ellipsoid is WGS84. Then these are the different ellipsoid. So as I already discussed about this long back, so as I told you, this GPS, Galileo, GPS, GLONASS, Galileo, they all are falling in UC L band only, except this S band and C band. So Galileo is going to have this C band also in maybe operational hour. It will be coming soon, and S band is available with INSS satellite, all the INSS satellites. So these are the code wave, and this is the carrier wave. So it is like a Bernoulli calipers. If you have seen Bernoulli calipers, it is the precision is like that only, subdecimal. So you can go 4 decimal and all. So you can have very precise information about the data. If multipath is taking place, obstruction is taking place, cycle sleep is taking place. So how this cycle sleep is getting restored, how the signal loss is getting restored. Our multipath is means we are attenuating, we are reducing the attenuate this multipath data from this observation data. So all this can be done accurately with the help of carrier wave data. So when we talk about the satellite system, so it comes with the 3 segment: space segment, control segment, and user segment. So this is the space segment. You can see the block 1, block 2, and 2A. So these are the evolution of the GPS satellite, GPS navigation satellite. So this is completely different from the other remote sensing satellites, because other remote sensing satellites, they are acquiring the 2D image, and some are this sun synchronous, and some of like SAR satellite, they are emitting, they are continuously transmitting this electromagnetic wave of lower frequency microwave range, and some satellites, they are receiving this emitted ground thermal this infrared band they are receiving on their satellite. So but this is very very unique mission, and this again this grace is means unique than this also, because they are not receiving any signal, they are only receiving the gravitational changes which is happening on the earth. So they are detecting in the form of the satellite is getting accelerated and decelerated. So by the help of that, with the help of that, they are able to measure the gravitational potential around the earth. So but here it is continuously sending the electromagnetic wave on the this earth to receive by the antenna. So that's why these all missions are very unique and very systematic. So you can see this is the 4th civilian GPS signal, very very accurate and very precise, designed to enable interoperability between GPS and international satellite navigation system. This US and Europe originally developed L1C as a common civil code for GPS and Galileo. Japan and China Vedu system are also adopting L1C like signals. The main difference between GPS and GLONASS is that the GLONASS, each satellite has its own frequencies but same code, whereas GPS all satellites uses the same frequencies but have different codes. So this is the major difference between GPS and GLONASS. And these are the different these frequencies, mission duration, lifespan, and this precise P. Earlier it was embedded in the this block 2A, then block 2R, then 2RM. So there were so many this configuration was adopted over the time. You can see earlier there were course versus acquisition code on L1 was there, and this was not so accurate. But now these days this L1C is very accurate, and it is good, and it is giving more accurate information about the navigation and this location. Then this is another. So in this block 2 are 10 are operational, this block 2RM is 7 are operational, second F 12 are operational. So like that, GPS 3, this is the very latest latest navigation mission where 2 are operational, 2 satellites are operational. Then these are the GLONASS evolution in the satellites. You can see the GLONASS and GLONASS M, GLONASS K, GLONASS K2. These are there, and there are 3 orbital plane, and number of satellites in a plane 8. So that's why 24 total satellites are there, and these are the orbital parameter, and this whatever the satellites installed during 1982 to 2005 all were decommissioned, and this 2003 to 16 they are all are in use. 18, 11 and 18 design and maturation based on in orbit validations, and 17 plus in development. So these are the configurations and informations about the GLONASS. These are some informations, you can go through that. Then this, as I told you, this user segment, these are the user segment, these are the control segment, master station and monitoring station, and this is the space segment. How the satellites has been placed in the orbit. So you can see these space segments mainly satellites, user segments means receivers, and control segments means monitor and control stations. So these are the thing, and this coordinate reference is WGS84, and this mission control center operations at Shreveport, formerly Falcon, AFB, Colorado Springs. So these are the orbits, and they are inclined at, with respect to your equator, they are at 55-degree angle, inclined, they are inclined by 55-degree angle. These are the 6 plane, and 4 satellites in each orbit, so that's why 24 is there. And this is the elevation, so these all are there. I already explained about this. These are the control segment. So you can see these master control stations. This is the master control station, then monitor stations. So these are the monitor stations, and some ground antenna. So these are the ground antenna. So here you can see these are the information about the now the latest one is it has been enhanced too much, the GPS control segment. So master control stations here only, it's Colorado, but ground antenna has been increased, so many ground antenna, and then Air Force monitor station is there. So these are the Air Force monitor station, then alternate master control station is there. So some this alternate this is also one only, then second remote tracking station is there. So these are the stations, and then NGA monitor stations are there. So these are the NGA monitoring stations. So then master control stations responsible for collecting tracking data from the monitoring stations and calculating satellite orbits and clock parameters. Then five monitoring stations responsible for measuring the pseudo range data. This orbital tracking network is used to determine the broadcast ephemeris and satellite clock modeling. Ground control stations with antenna S-band uplink responsible for upload of information to satellite vehicles and routine maintenance. They are doing by all this control segment. So these are the architecture of the control segment, means the telemetry, tracking and commanding stations. Then central clock, then laser tracking stations, SLR. Some stations are monitoring this SLR. ULS is there, uplink stations is there, monitoring stations are there. So because these all are very much required to keep a balance between the this satellite orbiting, providing the accurate signal, providing the accurate ephemeris informations. So all these are very accurately required. So these control segments are very nicely handling and monitoring all this controlling all this task. The GLONASS satellite signal identifies the satellite and provides position, velocity, acceleration vectors at a reference epoch to compute satellite locations. Synchronization, beat, data age, and satellite health. So this GLONASS time from UTC, formerly Soviet Union, now Russia. So almanac for all other GLONASS satellites are available. Unlike GPS, all GLONASS satellites transmit the same code at different frequencies. They derived signal timing and frequencies from one of three onboard cesium atomic clocks operating at 5 Hz. So, for example, L1 is 1602 MHz plus n into 0.5625 MHz, where n is the frequency channel number. So 0, 1, 2, 3 like that. So L2 is there. So like that it is calculating the L1, L2 and other frequency. So the user segments. So there are so many users. So as I told you, the ship, aircraft, your airborne surveys, vehicles, medical vehicle, your this civilian vehicle, private vehicle. So then army, defense, and then researchers. So many people are using these days, and it is solving the problem very efficiently. So why GPS? So as I told you, it is weather independent. Rain, fog, snow have no effect on the signal. Doesn't require line of sight. Then give high geodetic accuracy. Then can be operated day and night. Economical advantages. Then common coordinate system. Wide range of applications. Then competitively priced and quicker and requires less manpower. So these are the advantage of GPS. How it works. So it is, I told you, trilateration based ranging measurement is there. So reference station is there, and they all are moving at 4 km per second, and it is continuously tracking the satellite. So GPS, we use the GPS receiver, detect the one-way signals from the several satellites. Each transmission is time tagged, and I told you it is producing the reply signal. So when it is going and fitting on the replica signal, this transmitted signal, time is not matching, and time phase difference is there, our time delay is there. So out of phase signal is getting out of phase. So we have to reduce this out of phase, and we have to bring into in phase signal. Then time of travel is compared with to the time of transmission. The delta t is multiplied by the speed of light to obtain the range. So this is the formula to estimate the range between the satellite and the antenna. So each range puts the user on a sphere about the satellite, intersecting several of this yield a user position. So this is how it is happening. So this receiver is autonomous mode, provides navigation, positioning accuracy of about 10. SA is off there, and 200-meter SA is on, so it is basically compromising. So when SA is on, so you see the accuracy is not good, about 100-meter, due to the effect of GPS error. But when SA is off, so error is less. But there is no SA no more. It is completely resolved. And now I told you L1C is coming, so it is very accurate. So I think I should stop here, and tomorrow I will start